So if you know that the limit of the absolute value is 0, then does that tell you that the limit of the function itself is 0? Right? So for example, so sometimes if you're thinking, what do they mean by this? Let's just make an example. We know that the limit of absolute value of x is 0, right? Do we also know that the limit of x is 0 as x goes to 0? As x goes to 0, does x go to 0? Yeah, that's true, right? That's true. So here's one example, right? Here's a function, its absolute value goes to 0, and the function goes to 0, right? Can you think of a function where the absolute value of it goes to 0, but the function doesn't go to 0? The absolute value of it goes to 0. Can one have so that the absolute value goes to 0, but the limit of the function isn't 0? Do you think that's possible? Actually, it's impossible because the question is asking you to show that if the absolute value is 0, then the function has to be 0. But maybe it's good exercise to think, right? Can you think? Does that maybe you don't believe the book? Can you imagine a function where the limit is not equal to 0, but the limit of the absolute value is equal to 0? Right? If you think about it, you start finding that you can't create it. You can't do it, right? Hard to do. In fact, it's impossible to do. And so they're asking you to try to explain why that happens. And one way to explain it is to use the pinching theorem. Okay, so in fact, suppose you know, say we know, suppose we know that the limit of the absolute value is 0. Right? Okay. Can anyone see how to use the pinching theorem to see that if the limit of the absolute value is 0, then the limit of the function must be 0? Can you trap the function? Like the pinching theorem is all about trapping, right? Can you trap this thing between two other functions, both of whose limits go to 0?
Would it just be negative absolute value?
Yeah, and?
Equals 0, limit is 0.
Yeah, so negative, certainly below, we know that this is going to happen, right? And what about above? The absolute value itself, right? The absolute value itself, right? So, right, you can, here's one idea. You know that, for any number, right, you take any number that's certainly smaller than its absolute value and bigger than the negative absolute value. Right? The number is going to lie between there and there. Right? Okay. So and we know that the limit of this, we know that the limit of this is 0. Right? The limit as x equals to c is 0, and we know the limit of this as x equals to c is 0. Right? Right? And so what does that tell you? By the pinching theorem, the limit of the middle guy must be 0. Okay. So if the limit of this is 0, then the limit of the function itself must be 0 by the pinching theorem. The end. Okay, you see that? That was how one could use the pinching theorem to see that this follows from this. Stefan?
Could there be a situation where f of x equals something like the output is something negative, and when it's inside the absolute value, becomes a positive? No, never mind.
It's still going to work out. Still going to work out. Right? For any number that you have, positive or negative.
It's hard to picture for me. I wouldn't expect.
Say it again?
It's hard to picture for me. Once I saw it in the answer, I saw that the possibility, but I still couldn't definitively believe it. I can't really picture it.
You still don't believe that a number is trapped between its absolute value and its negative absolute value. So it's hard to sometimes.
How do you prove that? Because for me, if it's just as simple, I can't really get it.
Yeah, so part of the, sometimes things are hard to imagine.
Mhm.
Thing to do is to make it concrete. Put in a number,
Okay.
right? Just say, yeah, let's suppose that f of x is 5, right? Well, 5 is certainly trapped between the absolute value of 5 and negative the absolute value of 5, right? Or if f of x is, suppose f of x is some negative number, negative 1. Well, negative 1 is certainly trapped between the absolute value of negative 1 and negative the absolute value of negative 1.
And for pinch theorem to work, it'd still be or equal to those
Yeah,
values? Okay.
yeah, right. Because all you need is that you know, you have you know, it could be equal to one of them.
Mm-hmm.
You know, it just has to be less than equal
Okay.
to one and greater than equal to the other.
Thank you.
Yeah. Yeah. So yeah, a lot of these things, you know, it's abstract, right? It's abstract. One useful thing is to just make some concrete example, and that'll give you a better sense of what's going on. So that's one strategy. Okay, does that make sense to everyone? How you would say it? You'd say, you know, right? They're saying, try to explain why if this happens, then this happens. Well, if this happens, then you know that the limit of this is 0, and you know that the limit of this is 0. Well, f of x is trapped between those two things, so by the pinching theorem, f of x must also go to 0. Okay? So, not in hindsight, pretty straightforward, right? In hindsight, not too bad, I hope. Of course, you know, before you do it, it's hard. Then after you do it, it's easy. Before you do it, it's impossible. Yeah, but you keep on trying. So one thing I said at the very beginning of the course is that, you know, some problems will take some problems will not be immediate, right? In high school, it may have been the case that you got a problem, you looked at it, you solved it. It took about 1 minute to do every single problem, right? Or maybe, you know, at most 2 minutes, right? But now you have to think of it, right? And thinking actually involves some time, right? So it's not, I'm just going to follow some rules and you know, and get an answer, but rather you have to think, right? And that's what you're here for, right? You're not here to learn how to follow some rules, I hope. Right? Are you? No. Stefano? Stefano, are you here to follow rules? Get out! Yes,
my question was, I think the second one,
yes.
that was also still from part 2, from 2.2. It was like saying to follow theorem number 8 or like theorem number 5 or something, and the answer in the answer book just like made no sense to me. Like
Okay.
you were just doing things that I thought like had nothing to do with how you what's like allowed, and I didn't know where it came from.
Okay, let talk to me after class. Actually.
Okay.
Yeah, let me.
Okay, sounds good.
Yeah, I want to get on finish some stuff. Okay. Okay. So there's one thing that we did at the very end, which was this thing about continuity, and composition. Okay, and what I said was that if you have an F continuous at C, and you have G continuous at F of C, then G composed with F is continuous at C. Okay. So remember what continuity means. Continuity means that when you're evaluating a limit, you can just plug in the point. Okay. That's what continuity means. When you're evaluating continuous functions, have this nice property. They are the functions that, if you're evaluating a limit, you just evaluate the function at the point, and that's actually the limit. Okay. And so what this is saying is that, for example, right, if we ask the limit of the square root of sine of x as x goes to pi over 2, well, you say, well, look, sine is continuous at pi over 2, right? Sine is a continuous function. Sine was continuous everywhere, we said. Well, it's certainly continuous at pi over 2. The square root function is continuous at sine of pi over 2. What's sine of pi over 2?
1.
90.
1. 9?
I was going to say 90, but.
Sine of 90,
Yeah.
so 1. Yep. Right? The square root function is continuous at 1, right? And so the square root of the sine is continuous at pi over 2. Okay, so the limit is just going to be the square root of the sine of pi over 2. Right? You can just evaluate it. This function is continuous, so you can just evaluate it at that point. Right. Yeah, go ahead.
Can you explain why that 1 is pertinent for the sine of pi over 2?
Well, we need, we're looking at a composition of functions, right? We're looking at a composition of functions. Sine and the square, sine followed by the square root, right? Okay. And we're wondering if this composition function is continuous, that is, we can just evaluate it at pi over 2 to figure out the limit. Okay. It turns out that, well, where does sine take pi over 2? It takes it to 1, right? And then you take that sine of 1, right? I'm sorry, you take the square root of 1, and that takes that to 1, right? So what's happening is the sine is continuous at root 2, at pi over 2. The square root is continuous at 1, and so this guy is continuous at pi over 2. Okay, so to evaluate, right, so for the sine, to find its limit at pi over 2, you just evaluate and you get 1. For the square root function, to find its limit, as something gets close to 1, you just evaluate it at 1 and you get 1.
Okay.
Okay, and so the composition is going to be continuous at pi over 2. So that's this business here. F is continuous at C. G is continuous at f of c. Right? So here's C. Here's f of c. And then here's g of f of c. Right? F, right? The composition function, g composed with f, takes f to c to f of c to g of f of c. Right? And so just to, right, so you can compose, a composition of continuous functions is still going to be continuous if they're continuous at the right points. If the functions are continuous everywhere, that's great. Then you don't have to worry about where, you just know that the composition is continuous everywhere. Yeah, Mariah.
Wait, so if you were to draw a picture, it would just be the unit circle with the hole on top, like where 1 is?
I'm not going to draw. I don't want to draw that picture right now because that's gonna confuse everybody. I think.
Okay.
Rather, you think the sine is something that takes in a value and spits out a value. It's a function. Okay. And then you've got the square root function, takes in a value, spits out a value. Right? It's also a function. So we're thinking of it like this.
Okay.
So is it continuous because that 1 is the same on each of them, or just because that we have an answer on the third one?
We actually saw this in the previous. We actually mentioned this in the previous section that the sine and square root functions were continuous everywhere they were defined. So that's why they're continuous.
Okay.
Yeah. Yes, fun.
What would we say about the limit, and would we have a problem where it's square root of sine of 3 pi over 2?
Square root of sine 3 pi over 2.
Yeah.
Yeah. So okay, so right, the sine then, right? So here we have sine is continuous at 3 pi over 2. Right? But the square root is undefined, right? For sine of 3 pi over 2. Right? So our theorem doesn't say anything. It'll say, I don't know. Right? I can't tell you it's continuous. I'm not going to say it's continuous. And in fact, the function isn't even defined there.
Why is it undefined?
Because this sine of 3 pi over 2 is negative 1. And you're taking the square root of negative and negative.
So you would say it's not continuous at that point?
Well, it's not even defined at that point, so let alone continuous.
Okay.
Yeah. But if the square root function had a discontinuity somewhere, it doesn't. The square root function is continuous wherever it's defined. But suppose you had some function that had a discontinuity there, right? Then you wouldn't be able to say that your composition is continuous. In fact, your composition is probably discontinuous. So, but as long as these two things happen, then you can say I'm allowed to evaluate this guy at the point to figure out its limit. Okay. We just talked about the square root function in my other class. So my other class is a course in something called complex analysis. It's sort of what would happen if you did calculus but with complex numbers. And it turns out that it's a lot more complicated, but a lot cooler. And in the complex world, there's a way of defining the square root function as a single function on a double complex plane. Okay, so that on one plane you have the negatives, basically what are like the negative square roots, and on the other plane you have the positive square roots, and they're linked together by some slice. And you pass through the slice and you end up in the positive world. You pass through the slice again, you end up in the negative world. Okay. So anyway, the square root function is actually a lot more cool than you might imagine. And just to this is actually the origin of Alice Through the Looking Glass. The author of Alice Through the Looking Glass was a mathematician, right? And he thought, oh, this would be a great idea, right? You have these two worlds. You pass through the slice in this one world. You end up in this world where everything is backwards. You pass through the world again. You come back to your original world. Right? So that's the beginning of Alice Through the Looking Glass, and its long, distant descendant, the Matrix. Right? You remember, so Neo is actually stuck in the fake world. Right? How does he get to the real world? He touches a mirror, and the mirror flows over him. Right? And then he ends up in the real world.
I know which one's real.
Hey, put that up. Now the logarithm function is even crazier than that. Instead of two planes, you actually have an infinite sequence of planes. And as you pass through one, you end up to the next one, to the next one, to the next cut. You can go backwards down through the cuts. Right? So we're sort of, as mathematicians, we're sort of thinking, what's going to be in matrix 2? Maybe it's the logarithm, right? But it wasn't. It stayed with the square root function. Okay. Okay. So finishing up the last part of 2.2 or 3. Excuse me. There are these things that I'm going to call deep properties of continuous functions on R. Okay. And they're deep because we're not going to explain them, actually. They're deep because they rely on something that's very subtle. Basically, the difference between R and Q. The difference between R and Q. Okay. Yeah. Anyway, I'll try to make what that difference is clearer as we talk. So let's start off with a definition. So if you have some function on an interval, if f is continuous on the open interval AB, and it's left continuous on at A, and right continuous at B. Right, so the picture is like this. Here is A AB, and you have some function that's continuous between A and B. It's continuous between A and B, and further, as you approach from the right, you actually get the value there, right? The limit of f of x as x approaches A from the right-hand side is f of A. And similarly, the limit of f of x as x approaches B from the left-hand side is f of B. Right, so it's right continuous, oops, I got it backwards. It's right continuous at A and left continuous at B. Right, it's right continuous at A, left continuous at B. Then we say f is continuous on the closed interval AB. Right. So continuity on a closed interval is what the notion we're introducing here. Okay. You're continuous at every point in the open interval, and you have this sort of half continuity at the left and right endpoints. Okay.
How do you know that it's a closed circle instead of an open circle?
That's what you need to happen.
Okay, so that's part of, okay.
Yeah, that's part of it. You need it to be right continuous at A. In other words, you need the circle to be closed here, and you need to be left continuous at B.
Wait, it could be, continuous, okay.
Continuous.
Yeah.
Yes, Stefan.
It's kind of the same as your question, but like you start with the open interval and then ended with the closed.
Mm-hmm.
I know where I don't know what was it an open interval for?
All we're saying is that this is what we mean. If we say continuous on the closed interval AB, what do we mean? We mean that it's continuous on the inside, and that you are continuous from the right side here and from the left side here.
Okay.
That's just what we mean.
Okay.
That's a definition of this.
Okay.
Okay. Okay. Now that definition allows us to state some key properties. The first is called the intermediate value theorem. So say f is some function on a closed interval. If when f is continuous on that closed interval, and 2, f of A differs from f of B, then for any value between f of A and f of B, there is a point in AB where that value is attained. Right? So for any intermediate value, there's a point where that value is attained. I'll let you finish writing this down, and then I'll explain it graphically. Okay, everyone done? Okay, so here's the picture. You have some function on AB. F of A and f of B are different. F of A and f of B are different, and the function is continuous on the closed interval, right? So you have some line going from here to here. Okay. What this is saying is that it says if the function is continuous and f of A and f of B are not equal, then for any value between any value gamma, say, let's call that value, any value gamma between f of A and f of B, there's a place where the function reaches that gamma. there's a place where the function reaches that gamma. So if I choose gamma to be this value, well, look, there's a place where f of c equals gamma. Right? If I choose some other value, well, there's a place where where f attains that value. Right? For no matter what value between f of a and f of b I choose, there's a place where I'm going to hit that value. Okay. So given any intermediate value, there's a point where that intermediate value is attained. Right? Given any intermediate value, there is a point where that value is attained. Okay, so here's a simple example of the application of this theorem. So the question is, does x cubed minus x squared plus 1 have a root? Is there a real number satisfying x cubed minus x squared plus 1 equals 0? Okay. Is there some number that satisfies this equation? Right? You made up some equation, and you're wondering if that thing actually has a real root. Okay. The intermediate value theorem. The intermediate value theorem will give us an answer. Right? You say, well, look, consider, let's call this thing f of x. Call this thing f of x. Consider f on, say, like negative 10, 1, or negative 10, comma 0. F at negative 10, what's that? Well, that's negative 1,000 minus 100 plus 1. Right? Negative 1099. Right? What's f at 1? F at 0? Well, f at 0 is just 1. So what can you conclude? You conclude that at some point between negative 10 and 0, f crosses the line, right? F attains the value 0, right? So f must attain 0, right? 0 is intermediate to negative 1099 and 1, right? So at some point, somewhere on negative 10, comma 0, right? There's a root somewhere in there. You don't know what it is, but you've narrowed it down to at least you know it exists and you roughly know where it is. Yeah, Claire.
How did you know to do that interval?
I just thought about it, right? You just look at it and you say, well, I'm trying to figure out if this guy ever crosses the 0, right? Well, here I've got this x cubed. So it's one of these things where you have to look at it, right? You look at it and you think, oh, look, x cubed, if I choose a gigantic negative number, that cube is going to be a huge negative number, right? So I'm trying to find some interval where the thing is both negative at one side and positive at the other side.
Okay, so you know it's going to be negative if you have a negative number, and then
Right.
0 would make it
Right.
positive. Okay.
Right. Yes, sir.
When you say root, you mean the
A 0.
x?
Yeah, a point where the value is 0, where the function is 0. A point where it crosses the, right, so a point where it crosses the axis. A point where it crosses the x-axis.
That's the root?
The root, a 0, like a 0 of a polynomial,
Mm.
a root of a polynomial.
Okay.
the same thing. So root x is a root, a is a root of a polynomial means the polynomial is 0 and x equals 0. Right? It's a place where a root or a 0 So yeah, so this allows you to one use of this is showing that you know that you can find that roots exist. Yeah, go ahead.
Can you overshoot b, in terms of trying to find that interval?
Yeah. So I could have chosen say 10 on this side, and that'd be fine because then I'd have 901 on the other side. That's great, right? On the left side, I've got a negative number. On the right, as long as I have a negative number on one end and a positive number on the other end, I know it's going to hit 0 in between.
So it's not important to narrow it?
Well, it's important if you're curious as to what the root actually is.
Okay. But otherwise it's...
Yeah. So the question was just, does it have a root? And we can say yes, it does.
Cool.
You could, if the question were narrow as much as you can, the interval to where the root lies, then you'd have to play around more.
Okay.
And like if I ask you where, find an interval of length 1 where this happens. Well, then let's try -1. So -1 would be great, right? Because you get -1, -1, +1, so that's -1, right? So -1 would also work, right? That's a -1, it's actually -1. So in fact, we know it lies between -1 and 0.
But that's only if they ask us to narrow it down.
Yeah.
Otherwise, we're okay.
Yeah. Okay. Other questions? Okay, so let me point out something funny. Suppose we're in Q. Okay, suppose we are the Greeks. Okay, we don't know rational numbers. And somebody draws this picture and says, I'm going to draw 2 lines like this. Right? This length is 1 and this length is 1. Right? So here's my Q and here's my Q. Right? I've got Q against Q rather than R against R. Okay. Is there a number? Is there a number where this line crosses that line? Is there a number where this number crosses that line? Crosses the line?
Yes.
It looks like it, right? It looks like it. Right? No matter how fine your ink is, it's going to look like a solid line. But in fact, the number would have to be the square root of 2, right? Which is not in Q. So there's a hole there, in fact. Right? There is no number. There is no number there if we're Greek, if we're the ancient Greeks.
Why is it root 2?
Oh, just because this is, if I drew it like this, if I drew it like this, then a squared plus b squared equals c squared. Right? So that length is root 2. So yeah, so there would actually be no number where this line crosses the axis. Okay. So the intermediate value theorem wouldn't work. There is no intermediate value theorem for Q. Okay, but there is an intermediate value theorem for R. So intermediate value theorem fails for rational numbers in rational numbers. Another subtle property of the real numbers. Question?
No, I just forgot what the symbol was for irrational numbers.
Irrational. Well, some people use like this not in Q, or some people use a Q with a
So
tilde.
Q is rational and R is real.
That's right. That's right. Some people use Q with a C on it, the complement of C. the complement of the cubes. Okay. So subtle property number 2. We need a notion. Here's some function on some set. Okay. We call a minimum of f on E. Yes?
What's capital E?
It's just some set. So like some set in the reals. Yeah, if you like, you can think of it as some interval or some collection of points. You know, some set in R. We call alpha a minimum of f on E if f of alpha is smaller than all other values. And in case I haven't introduced it, this upside down A is means for all. So if f of alpha is smaller than f of x for all x, then we call alpha the minimum. We call f of alpha the minimum value. So for example, if I have a function, here's my function. Okay, so here it is, not that exciting, right? My function is f of x equals x, and I'm looking at it only on the points 1, 2, 3, 4, 5, then this is going to be the minimum, right? 1 is the minimum value is 1. Right? The smallest value attained. Okay. Similarly, maximums. Okay. Yeah, all right.
If you have like a whole line, just like y equals horizontal, would there be like an infinite number of minimums?
Yeah, could be, yeah. So if you have a constant, say, constant function, then all those values are the minimum value, but they're all also the maximum values. Yeah, by this definition. Yeah, okay.
Wouldn't there not be a minimum for f of x equals x because it keeps going down?
Well, I'm only looking at it on 1, 2, 3, 4, 5.
Oh.
So this is my set. This is my E, my set E. Okay. So here it is. Right.
If it wasn't defined though, it would not have a limit.
Right. So yeah, if I'm looking at f of x equals x, and x is allowed to range all over R, then there's no maximum and there's no minimum, right? No matter what point you choose, right? There's always a bigger value, and no matter what point you choose, there's always a smaller value. Right? Okay, so you're not guaranteed a max or a min. Okay. Since you are bringing this sort of thing up, what if I change it to say 0, 1? X is in 0, 1. Is there a minimum value? Is there a maximum value? So where do you attain the minimum value?
Oh, wait. Is that just one point or is that minimum?
Where's the minimum value? Where do you attain the, right? So you want to find, it has to be a point where the value is smaller than all other values. Is there a point? Right? Is there a point where you attain a value that's smaller than all other values? Some people are nodding and some people are shaking.
Yeah, it's still a line, isn't it?
It's still a line. It's still a line. So, so then I would ask you, like, if you think there is a point where the maximum value is attained, where is it attained? Where is the maximum value attained?
1, 1.
No, you're not allowed to use one. You're not allowed to use one. X is only on the open interval 0, 1.
I see.
I was thinking like infinite. Yeah.
Right. So no matter what value you choose, I can always choose one that's a little bit bigger than that. Right. So there is no max and no min for this function. Okay. So no min, no minimum, no maximum. Okay. Okay. But here you have something that is extremely very important. It's called the extreme value theorem. If you have a function on a closed interval and it's also continuous there, then you're guaranteed a minimum on AB, and you're also guaranteed a maximum. You're guaranteed one. Okay, so right, if you're on some closed interval AB and your function is continuous, well, there's going to be some point where a maximum is attained. There's going to be some point where the maximum is attained. There's going to be some point where the minimum is attained. Okay. You can't. It's not the case that you could get arbitrarily close to something but not attain it. Okay. This is actually really subtle. Here, you can get arbitrarily close to something and never attain it. But here, we're actually going to attain the maximum value. Okay. And this will be key. This fact will be key when we start talking about the derivative later on. Okay. Madeline, please.
What about like on this equation where you have what looks like 2 minimums?
This one? It's okay to have multiple minima, right? If you have a straight line, then everything is a minimum.
Um,
That's all right.
You're guaranteed in this one.
Yeah, right. They're all minimum. They're all minimum. They're all maximum. Right. Yeah. So you're guaranteed A, and there may be more than one. Right. Clear?
That's what
That was your question. Yeah. It doesn't say you're guaranteed that there's one and only one, but you're guaranteed one. Any other questions? Okay. So these properties of continuous functions may seem sort of esoteric right now, but actually they are particularly the second one are what everything builds on in the future. Okay. So when we talk about differentiability later on, we're going to be coming back to this repeatedly. We'll come back to the extreme value theorem repeatedly. So although I don't think there are many questions about it, there are no really good questions about it in the homework. There are questions, but not really good questions about it in the homework. Keep it in mind because it's crucial.